And I really have to thank the organizers for inviting me here. Brazil is a great place. IMPA is a great place. It feels like home somehow. Actually, I have to thank one of the organizers especially because this will be home soon. All right, so let's get right to the point. Let me start doing some very, very old mathematics. So I want to introduce a function that has been studied for several hundred years. And I'm going to use this for an excuse to introduce an ill manifold that I'm interested in. So let's say R is a ring. The Heisenberg group with coefficients in R, this would be the set of upper triangular 3×3 matrices. Actually, I don't like this thing divided in 6. Let's do this. Of upper triangular 3×3 matrices whose coefficients are in your ring. Under group multiplication, this is an nilpotent group. And if you have this thing, you can think of taking the complex Heisenberg group and mod it out with the integer Heisenberg group. If you give me, say, a representative here, something of this form, you can map it down. By the way, I should probably make a warning. I reserve the right of messing up a few factors of 2 pi, or if you want, I'm going to be working in units where 2 pi is equal to 1. But if you give me such a representative, I can map this to e to the a, e to the c. And these guys are coordinates on c star cross c star. And now you see that I don't really care about 2 pi's. And here's an idea of the line, a very old idea. Let's take P1 minus 3 points. Let's take a global coordinate here, Z. And let's map this to C star cross C star via Z 1 over 1 minus Z. I mean, this is well defined because I took out these points. The great thing about this is that, well, this co-cycle here gave me a line bundle over C star cross C star. This is not only a line bundle, but it's a line bundle with a connection. It's a non-integrable connection because I can pull back the 2 vector fields on C star to get to this Lie algebra of the Heisenberg group. And since this Lie algebra is non-commutative, the connection on this bundle is non-integrable. But I can pull back by this map, that line bundle, to obtain a line bundle on P1 minus these 3 points. This is the canonical bundle with the canonical unipotent connection on P1 minus 3 points. And the beauty of this is that we can find a global section of it. So we can find a map that makes this diagram commute. We already know what these 2 components should be. So this should be log of Z, log of 1 minus Z. And what should go in this spot, let's call it L of Z, that has a name, is the Rogers dilogarithm. Which has an integral. I may get this with the wrong sign. Perhaps it's 1 over 2. An integral representation of the following form. Here you need to choose a path between 0 and Z. There's going to be a couple of branch cuts. Particularly, this has problems at 0 and at 1. So there's a branch cut here. There's a branch cut there. And whenever you go around 0 or 1, you pick up some monodromy. And I don't need to tell you what monodromies those are, because I'm telling you that this diagram commutes. This map is a well-defined map in the quotient. Probably should go like this matrix. Now, this function, okay, why the logarithm, perhaps? this function has a couple of nice properties. Let me introduce the older function. So let's say this function is the dilogarithm of z plus 1/2 log of z log of 1 minus z. And this dilogarithm is Euler's dilogarithm. This was defined originally. This is the way Euler was studying it, as a sum of zk over k squared. And then you recognize, oh, this converges, of course, only here. Here you recognize that if instead of a square I had a 1 here, that would be the exponential of the expansion of the logarithm. And if you put larger numbers here, you get polylogarithms. This function, the Rogers dilogarithm, has a couple of properties that are interesting to us. I'll just write just a couple of them. The point here is that this is a constant. In my units, I can put this to be 1, but I think here that's one identity. And the most important identity this function satisfies is called the pentagonal identity, and somehow is the measure of this function failing of being a logarithm. So this should be 0 for a logarithm, but now is, if I am not wrong, it should be z. All right. So that's everything I need from the logarithm, from the dilogarithm. And this function, I mean, the whole thing here, I just wanted to introduce this nil manifold that I want to study, or a real version of it. All right, so that's as much as old mathematics. Let's go now to really old physics. I need to mention something about Poisson, I guess. That'll do for a while. Okay, so as a form of loose introduction, let's say you give me a manifold M. We're interested in studying the movement of strings in that manifold. So the position of such a thing would be given by a point in the loop space of your manifold. If you want to look also at their speed to get phase space, then that'll be a point in the cotangent bundle to the loop space of your manifold. Yeah, so let's finish using this. And this manifold being the cotangent bundle to a manifold, this is a symplectic manifold. Therefore, if I cook up any space that I would call functions on this symplectic manifold, whatever this is, this should be some form of Poisson algebra. And I'm happy that I don't need to define it, because here I would be lying. But our interest is in quantizing this. No. I really wanted to have T star of the loop space, and everything here is going to be formal in a second. That's why I'm being extremely loose. Soon I'm going to even pick coordinates on the loop space. And I'm going to think on M being a flat tori. So but phase space is the cotangent bundle to the loop space, not the loop space to T star. We're interested in quantizing this. And whatever quantization is should be some form of associative algebra. And later I'll argue that our quantization is good in any way, because we can choose an element H inside of this algebra U and call it Hamiltonian. Whenever you have a Hamiltonian, you get some flow equations, and we obtain well, let's stress quantum because this is already on the quantized algebra. Equations of motion for the nonlinear sigma model with target M. So I don't know if this is enough, but this is something that you will want in your quantization. If you have a Hamiltonian, you wanted to obtain the equations of motion of describing how physicists would describe the movement of strings on your manifold length. Of course, this board doesn't say absolutely anything because this is quite loose and what Poisson algebra is. I have some very, very concrete examples in mind. I only care about M being tori, for example, or nil manifolds. And that will give me a precise notion of what these functions are. I'm going to restrict to local functionals of a precise form, and that will give me a model for a very precise algebraic model for what this is. This is what people call Poisson vertex algebras, or generalization of it later. And those admit quantizations, which is what I work with, which are associative vertex algebras or chiral algebras. These are different names for these objects. Okay, so I should have a caveat here for the physicist. Absolutely everything that I would say from now on to a physicist would sound like textbook. And it's true, actually, it would be in textbooks. But there's a twist. The word chiral there is quite misleading. To a physicist, when you say chiral algebras, they think on left movers. And some algebra the left movers satisfy. So it denotes some dynamical information of what is left move. Here, our meaning for chiral algebra, or this vertex algebra, is quantizing phase space directly. There's no dynamics whatsoever. Dynamic comes later when you choose a Hamiltonian. In particular, all this algebraic structure of this vertex algebra there is not the one that the physicist, even for the torus, is not the one that the physicist in the textbook would study. Nonetheless, you recover the whole usual algebraic structure a physicist would get with this procedure. Okay, so let's start our work. Okay, so now let's start being a little bit more precise. So we will start with the basic example of M being S1. I want to study how strings move in S1. So this guy is going to be now Z mod, R mod Z. And the loop space, so Dimitri, I think this should answer how formal I want to be. If I pick a coordinate sigma on the source S1, I can describe the general loop in the following way. Just by Fourier transform. This, I don't want to have 2 pi's everywhere, so Q is going to be e to the 2 pi I. This, I'm forgetting a 2 pi here as well. And the important thing of this expression here is that this number W is an integer number. And it just parameterizes in which connected component of the loop space of S1 you're living. This loop lives. There's Z connected components in the loop space. If you have your mapping from S1 into S1, is how many times you're winding around your target S1. And that's why this number here is called the winding number. X naught is also special because if I put sigma to be 0, I should be landing in one point in M. So X naught is not just any number, it's only well-defined modulo the integers. All the other guys are just numbers with some reality condition if you want your loop to be real, but I don't care about it. Okay, so general wisdom tells me that I should make a change of coordinates of this form to the sigma. And again, so this is kind of confusing from a physicist's perspective because this Z is just a formal change of coordinate. The physicists like to think on this Z that I'm going to write now as a coordinate on a 2-dimensional space that they call the worldsheet of the string. And that includes having some dynamical information. I don't care about it now. So this Z is just a formal parameter. Okay, so that's the most general coordinate. This is a local coordinate on the loop space 2S1. Okay, so now let's look at the conjugate momenta. If I only had one variable, just this X naught, say, as a coordinate on S1, then its conjugate momentum would be the coordinate along the fiber with these Poisson brackets. Well, now I have infinitely many of them, all these xn's, so the natural simplex structure on the cotangent bundle to the loop space to S1 would be just have infinitely many of these guys. Have an infinite dimensional Heisenberg algebra, just generalizing these commutation relations. And I can collect all of these coordinates along the fiber into just one distribution. So these are the two coordinates collected into a distribution, which are local coordinates on the cotangent bundle to S1. Now, all of these commutation relations here, the canonical commutation relations, you can encode them in the following manner. You can read them all from something like this. Here, Z and W are just formal parameters. These are just formal sums. You can expand them and bracket them both. And the way to read these commutation relations is as follows. You just grab the function 1 over Z minus W. This is a formal sum. If you expand it in the domain where Z is bigger than W, so this just means expand this in power series of W over Z. And subtract the expansion in the domain where W is bigger than Z. These are just two different sums. The difference is what people call the delta function. The statement here is if you look at the coefficient on this side of Z to the minus 1 minus n, W to the minus m, in this equation you will get just this equation. And people in my field tend to, when they look at something like this, they just remember what is the function that you're expanding into different domains. So people write this in the following way, and this is just a matter of notation now. So this is just a matter of notation saying, oh, 1 over Z minus W is what you need to expand to obtain this, and this just means this, which are just the canonical commutation relations. So this is the Poisson object that I want to quantize. It's an infinite dimensional Heisenberg algebra. All right. All right. So now it's an idea of the only person that I really want to give a reference is Chris Hall, who. I mean, this idea is probably older, but they worked it out quite a bit. This thing of doubling. Doubling space-time. So this is work of Chris Hall and company. The idea is the following. I mean, this is kind of shocking. You started with a classical system. These are just coordinates at the classical level. And this number W is already an integer. Even at the classical level, this W is an integer parameterizing how many times your circle is winding around your target. Now, forget about all this infinite dimensional business. Just at the quantum mechanics level, if you only had to do quantum mechanics on S1, you would have this coordinate x0 and the dual parameter, this coordinate p0. Once you quantize it, p0 we know becomes a momentum which becomes quantized. It becomes an operator, d by dx, which has an integer spectrum. So the idea was, okay, why can't we think of this W itself as a momentum which is conjugate to a coordinate? And indeed, we can do that by just integrating P of Z. If we defined a dual coordinate by this equation, so that now this x star expands in the same way as before. Now we have P0. Well, P0 is the coefficient of 1 over Z, so that's why I want to integrate. So all of these xn's are just formally the same thing as the Pn. Actually, it's just minus Pn over n. But the thing is that I added a constant of integration, which is this coordinate x star naught. And I'm declaring this coordinate to be dual to an operator whose spectrum should be this integer spectrum winding. So I declared this to be the case. And now I have winding and momentum. From now on, I'm going to write P for this. So this is momentum. And I have them in the same footing. So effectively, what we're doing is perhaps this is also related to your question, Dimitri. Instead of trying to quantize the cotangent bundle to the loop space to S1, we're just replacing this guy by the loop space to S1 cross S1. We're compactifying the fiber. Because it doesn't matter. We know already that the algebra we're going to get is the same. So now we have this coordinate x on one S1, which was our original target, and now we have this coordinate x star, which is, you can argue whether or not it has some physical meaning. All right, so now we can start quantizing this thing. And what do I mean by quantizing this thing? So first of all, notice that we have these operators. We want to, for quantization, whatever quantization is, we want a vector space, and we want each of these coordinates to be realized as an operator acting on that vector space. And we want to replace Poisson brackets by honest commutators. But it's kind of obvious what we need to do. We have P, we have this, we have x naught, we have x star naught, which I can think of these coordinates on the finite dimensional d star of S1 cross S1. And then I have all the others, x n's and x star n's, where n is non-zero. And this gives rise to a Heisenberg algebra, an infinite dimensional Heisenberg algebra. So how to find a vector space where these operators act? Just standard. The quantization of t star of S1 cross S1 is just L2 of S1 cross S1. And P and W act as vector fields. So we will have this guy acting as d by dx, and this guy acting by d by dx star. And here, if I have an infinite dimensional Heisenberg algebra, how do I produce a vector space where these operators act? Well, you can just take half of those, take a trigger representation for half those operators, xn, x star n. You declare it whenever these guys are bigger than 0 to kill one vector, an induced. And now here's where, and just take the tensor product of these two spaces. If you want a Hilbert space, you probably want to complete this. But here's where physics is quite different, actually. If you grab your textbook in physics, we're declaring annihilation operators to be xn and x star n, where n is bigger than 0. I think in a typical textbook in physics, you would want xn plus or minus x star minus n. So this is, I mean, the algebra we're going to get is isomorphic, but it's not really the same. Okay, so I should say, so we want these operators to satisfy some commutation relations. I should have said this before. We have this equation here that encoded all of our brackets, this infinite dimensional Heisenberg algebra there, except this one. So now I want to encode this one as well. Well, since x star is just an integral of p, it's natural that we would have this to be just the integral of 1 over z minus w. And when someone reads this in physics, they say, aha, you're looking at the lattice vertex algebra for the lattice z plus z star. And I mean, you're going to be even more asleep if I define what a vertex algebra is. But I want to give you a couple of properties that this guy has, because those are the ones that we want to generalize. And notice that at no point I chose any metric on any of the circles. So this is really a lattice. I'm using only the lattice defined in S1 cross S1. All right, so. Okay, so what kind of properties we can say? So not only we have this vector space V, where these operators act, this xn and x star n act, but we also have some structure, some algebraic structure inherently in this space, which goes as follows. Say you give me two functions. Say you give me just a function, f in a smooth function in S1 cross S1. So f is just a function of x and x star, just an exponential. You can replace this guy by the same function of x of z, x star of z that we already have. And this guy, well, x of z and x star of z were these infinite sums that we already represented acting on V. So this guy acts on the vector space V. So how is that construction? Well, this is the choice that we made when we chose half the space to kill this vacuum. It goes as follows. Say you give me the exponential. The typical function here is the exponential of mx star plus nx. And you send this guy to, well, I'm going to write something redundant, I guess. Mx star of z plus nx of z. Well, you can't really take an exponential because these are infinite sums, so I cannot take products. But you can take a normal ordered version of this, which means write this exponential formally, just products of infinite sums. But whenever you see an xn, which is bigger than 0, where n is bigger than 0, just move it to the right, so that it kills the vacuum. So it's a simple exercise to check that this construction gives a well-defined operator acting on V, depending on Z, of course. Okay, so what are the properties of this construction? The nice property this construction has is that you can look at, say, you give me two functions, f and g. So you have f and g, just two functions. You can look at the following. You grab g of w, you act on this vacuum vector, generating this representation. You act later by f of z, and you pair with the vacuum vector again. This guy, a priori, lives in the following field. Or you can look at these guys in the opposite order. And this guy lives a priori in the following field. Okay, so the axioms of a vertex algebra say the following. Say three things. One, both are expansions or both, let me write it the following way, both converge away from the diagonal. So they're both expansions of some functions of z and w away from the diagonal. The second axiom is both converge to the same function. So there are just two different expansions near different axes of the very same function. And the third axiom is that both converge to the same algebraic function. So they're just, say, functions on P1 cross P1 minus the diagonal that are allowed to have some poles on the diagonal. And if you just start adding more functions of S1 cross S1 and just put them more here, you would have this collection of functions on several copies of P1 minus all the diagonals where you're allowed them to have poles. And there's an action of the symmetric group because they both converge to the same function. So these are what people call correlation functions. And we're so naive that in our quantization, what I'm interested is in computing these correlation functions in different examples than S1. So essentially that's what a vertex algebra is. It's just this collection of functions on several copies on P1 satisfying these axioms. And just as an example of why this exponential business does this and how easy it is to make this computation, at least these 2-point functions. Let's do that example. Let's say I look at the exponential of m times x star of z times the exponential of n times x of z of w acting on the vacuum. How does one perform such a computation? Well, I needed to, this meant just commute everything that kills the vacuum to this side. So there's a lot of things that are annihilation operators here. I don't care because it's going to kill the vacuum here. There's a lot of things that are creation operators there. I don't care because it's not going to pair with the vacuum. So the only thing that matters in computing such a thing is what is the commutation between x star and x. And that's why we computed that. So we know that they commute as logarithm. So it's not surprising that here we will get the exponential of that logarithm. And we will get here a sine times c minus w to the mn, which is an algebraic function that may have a pole along the diagonal if I'm an nr of different sign. All right, so that's about it for very old physics. So now I want to carry out the very same thing in two cases. I want to do this in two very explicit cases. One case is when M is a 3 torus with a non-trivial gerb. But for me, this a non-trivial gerb here would mean just the choice of a three form, which I'll choose it to be the volume form on R3. This is just the x dy dz. And the other example is I want to look at M when M is a manifold similar to this manifold that we introduced at the beginning, the Heisenbergian manifold, which is the real Heisenberg group modeled out by the integral Heisenberg group. This is just an S1 fibration over T2 over S1 plus S1, but it's a non-trivial fibration. There's no gerb here. So notice that these two spaces are quite different. I mean, the loop spaces to these guys. On the first case, I have Z3 connected components. On the second case, I would have conjugacy classes of this group connected components. So they're really, really different spaces. But so the phase spaces themselves are going to be quite different. But we want to argue, and this has been known in physics for several years already. We want to argue that the quantizations are going to be the same. But the interesting thing of this approach is that if we can produce these algebras in the same way, without ever solving the equations of motion, we can just say, well, we have an isomorphism between these corresponding quantized algebras, and this isomorphism is going to intertwine the Hamiltonian on one to the Hamiltonian on the other. So we can state that they're T-dual without ever solving the equations of motion. Okay. All right, so let's talk a little bit about the first case, the twisted case. So the very first thing I need to say is how does the gerb enter? What does it change? And what it does is, whenever you give me a closed tree form on your manifold, you can change the symplectic structure on the cotangent bundle to the loop space. I guess Anton Alexev is here, so I should credit him for explaining us this current algebras. But let's see. We still have this. We have these three coordinates now. Local coordinates on the loop space. So this is just the twisted torus case. So we have three copies of what we had before. So this is xi. I is 1, 2, or 3. We still have the dual coordinates. Pi of z. Again, the same thing as before. Pi z to the minus 1 minus n. I is 1, 2, or 3. And we still expect them to be conjugate. So remember, this meant that we have an infinite dimensional Heisenberg algebra. That we denoted it this following way. But the statement is that whenever you give me a 3 form on the manifold, I can change the symplectic structure on the cotangent bundle to the loop space. And the way I change it is by, well, I'm going to describe you a different Poisson algebra between the local coordinates. So instead, before we had, and we still have, that all these xn's commuted, and also the pn's commuted among themselves. But now it's different. Now, the commutation between the pi's and the pj's, I can encode them all. This is the 3 form. So So let me explain what this Lie algebra is. So this is just a different Poisson bracket among the coordinates on the cotangent bundle to the loop space. Okay, so let me say a few words about this. So first of all, the big difference that we had with the previous picture is if I look at just the zero modes of this, so the P naught and the P naught here, what you will find out is this commutation. Let me say Pi, Pj. This is not. It's just H, I, J, K, winding K. And this is a six-dimensional, so the P's and the windings, so the Pi's and the windings, J's, span a six-dimensional Lie algebra, which is non-commutative. In our previous case, this was just a two-dimensional commutative Lie algebra. Now it's a nilpotent Lie algebra, which is the universal two-step nilpotent Lie algebra. So you have two momentums, P's, you commute them, you get a winding, and winding is in the center. So by the way, here's an easy way of finding quickly why the nil manifold plays a role there too. If you grab just you can see inside of this Lie algebra the brackets of both the twisted torus, a frame of T plus T star on the twisted torus with the current bracket, and also T plus T star of the nil manifold with the current bracket. So let me write that quickly. Let me write this quickly in the following way. I want to find the analog in this picture of what this doubled space is. And again, this was studied by Chris Hall and company. Now we're looking for these coordinates x stars. Before we did the following, we went from S1 to S1 cross S1. Now I want to go from T3. And I want to add this extra coordinates x star in such a way that, well, I want these P's to be their vector fields. Well, we have a good candidate already here on this manifold. So I'm looking for a six-dimensional manifold, and I have this six-dimensional Lie algebra, which is nilpotent. So what I would do is the following: take a Lie group, and the unipotent Lie group, unipotent Lie group, whose Lie algebra is this G. It's a six-dimensional Lie group. And we can take this, form this quotient. So this is a T3 fibration over T3. Non-trivial T3 fibration over T3. Our original T3 sits here. These are the coordinates xi that I had before. And now the fibers, the coordinates along the fibers, are what I would call x star I. So you see that if you look at left invariant vector fields, there's a frame of the six left invariant vector fields in this X, you would find this Lie algebra G. If you look at the frame of left invariant vector fields and left invariant forms on the torus, and the current bracket, all the anomalous terms vanish, you will find again that G. And if you look at the left invariant vector fields on the Heisenberg nil manifold and left invariant forms on the current bracket, you still will find this G. So that's how you find both of them inside of this six-dimensional guy. All right, so the issue is that we still have the vector fields d by dx star are well defined. The vector fields along the fiber are left invariant. But the vector fields d by dx are not. So the vector fields that are well defined here are these guys. So this suggests that if the relation among the basic scalar field and the momentum is not what I had before I had this, I had defined x star I to be just pi. And now we need to change this. We need to put as our definition of our field. And somehow this is perhaps the only new thing from a physicist perspective, is that just integrating these equations, these commutation relations, before we got logarithms, now we get that the commutation relation between x star I of z and, of course, x j of w. This is still the same thing that we had before. This is delta ij log encoding the fact that the p's and the x's satisfy the Heisenberg commutation relations, but now we have x star I of z with x star j of w. And here we find something of this form. Jk, winding k, dilogarithm of z minus w. So that's how the dilogarithm appears as singularities of the... Again, this means the same thing as before. Just expand these functions in different domains and you will get the usual commutation relations. All right, so now I want to quantize this. And the question is, how is this the same algebraic object that I had before if I want to find the representations of these operators, and what is the algebraic structure that it satisfies? Good. So the very basic question is, let's first find a vector space where all these operators act. Well, but we can do exactly the same thing as we had before. So before, we looked at this S1 cross S1. We had this two-dimensional commutative algebra, and we took a representation of the corresponding Kac-Moody type algebra. Here's the same thing. We have this finite dimensional Lie algebra G. We can look at loops into this Lie algebra G, and we can take a central extension of this Lie algebra. So this Lie algebra is the Lie algebra spanned by all these operators that we have so far. We have this windings i's, these pi's, the xn's, etc. So the commutation relations that are in the first board are just the commutation relations of this algebra, where G is the nilpotent Lie algebra. So we can do exactly the same game, play the same game we had before. We can start with L2. Before we took L2 of S1 cross S1, now we have this 6-dimensional nil manifold. Well, instead of L2, let's start with smooth functions so that this makes more sense. And induced from this algebra to the whole Lie algebra. So that's a vector space where all these operators would act with the same commutation relations. And the question is, does it have an algebra structure just like the vertex algebra we had before? And the answer is actually, because I'm surprised of the identities we find. I was surprised to see these kind of identities, at least in this context. Just the following. If you grab, let's take two of these examples. I mean, of course, it's kind of much more complicated now to deal with the algebra functions, because if I wanted to honestly commute, to honestly write down commutation relations for these functions, I would have to deal with the algebra functions on this nil manifold, and there's some rich analysis that you have to perform there, because whatever I did for exponentials before, now I have to do it for Jacobi theta functions. But so let's forget about the Jacobi theta functions part. Let's just only deal with L2 functions that are not continuous. So let's say I have the same thing that I did before. I take the exponential of m times x star. So well, now it's 3 functions. I need to pick 3 numbers. Let's say winding I, x star I of z. This is one function. The other function is exponential of winding prime I, x star I of w. And I act on one of these functions again, on the exponential. So I pick 3 different windings. These are 3 different lines. So this is just one function inside of L2, manifold x. And I pair this with the product of the 3 functions. And the commutation relations between these two is, I mean, the way to compute this is exactly the same thing as before. I just need to use the commutation relation between these x stars, which is right there. And when I read, is that this is the exponential of the volume of the tetrahedron spanned by these 3 windings. times the Rogers dilogarithm of W over Z. This is surprising because, well, it satisfies some of the axioms of the vertex algebra. First of all, this guy converges to something that is nice away from the diagonal. Second, if I do it in a different order, it does converge to the same thing because I can use this identity that this was a constant. So it's just modular rescaling. I can just make this constant 1. So if I make these functions in a different order, to have this action of the symmetric group of two letters in these correlation functions, I need to use that identity of the dilogarithm. But the problem is they don't converge to algebraic functions. I have to do some analysis. So in particular, if you start adding more functions, you would find line bundles on several copies of P1 minus all diagonals, and these correlation functions would converge to sections of those line bundles, but not to algebraic functions. And I guess at this moment I should write this as a conjecture, but the statement is if I wanted to do the same thing so if you want to have 3-point functions, I'm having problems checking this with signs. I'm going to just put 3 exponentials, span it, you will have 3 variables, z, w, and t. And in order to have an action of the symmetric group of 3 elements on the correlation functions, you will have to use the pentagonal identity that I wrote for the dilogarithm. Which is quite striking. All right, so let me perhaps finish in a few words. Let me just say something about the Heisenberg-Neal manifold, which I guess is surprising. Let me just say something connecting this. I mean something about the structure of the algebra of functions here. So forget about if I wanted to just do quantum mechanics on the Neal manifold. So we have now, let's just take this M to be the Heisenberg algebra, the Heisenberg group. So if we wanted to do quantum mechanics on this manifold, our Hilbert space would be, the Hilbert space here would be, well, just L2 of this manifold M. If you want to do string theory, well, then there's the infinite dimensional part. But forget about the stringy part. Just remember the winding number. And let's just take one copy of this guy for each winding. So that would be, the Hilbert space would be the sum over correlation functions over conjugacy classes of the Heisenberg group. Those are the windings of L2 of this manifold. On the twisted torus side, so with a gerb, what can we do? Well, instead of taking L2 of the manifold M hat, so let me just change this, I would do the following. For each winding, windings are just in Z3 now, you construct a line bundle. So for each winding is an element of Z3. You have this 3 form IJK. Whenever you give me a winding there, you can do the following. Say, construct a 2 form. Winding 1, dy, dz, minus winding 2, dx, dz, plus winding 3, dx, dy. And take it as a Chern class of a line bundle on your 3 torus, and take L2 of that line bundle. And this is naturally your Hilbert space. If you just forget about this infinite dimensional fuss, this is just quantum mechanics remembering the winding number. These 2 spaces, there's these 2 spaces, well, they're sums of Hilbert space. So it's naturally, of course, they're going to be isomorphic. But the statement is that they're naturally isomorphic. And they're both naturally isomorphic to this L2 of this double space. And the natural isomorphism is actually quite beautiful because a priori one doesn't guess that these 2 spaces are the same, but okay, so in this space, in this nil manifold, there's a natural basis of functions on the nil manifold. These are just Jacobi theta functions. And in this space, you have a 3 torus, you choose a line bundle, because of this winding. You have your 3 torus, you split it up as an S1 in the direction of the winding, and an elliptic curve on the other directions. This line bundle happens to be now a holomorphic bundle on that elliptic curve, and this space also has a natural basis of Jacobi theta functions, therefore. And these two bases of Jacobi theta functions are exactly the natural basis of invariant spaces here, of Jacobi theta functions on this nil manifold. So this is a matching up of the functions on the one side, and on top of that, with the natural computations of these correlation functions, what you end up having is that this space has a structure of a vertex algebra where you relax the condition of the correlation functions being algebraic. And the Hamiltonians match up immediately. So you can rigorously check that you have T-duality without ever solving the equations of motion in this case. All right? That's about what I wanted to say.